Hello, hello. My name is Maxim Jenihin. I'm an associate professor at TalTech Estonia, leading a research team for trustworthy and efficient computing hardware, and also coordinating the European twinning project TAICHIP. Today, here with me are Professor Cristiana Bolchini from Politecnico di Milano in Italy.
Pleased to see you, Maxim. Thanks for having me here.
Okay, and also Leticia Maria Bolzani Pöhls from the research center IHP Microelectronics in Germany.
Hello, thank you for having me here.
So, the focus of our discussion today will be the trends and challenges of AI chip design. As a recent trend, artificial intelligence is increasingly brought to the edge of the network and close to the source data and to the user, to the sensors, and that is establishing the concept of HAI. And specific to this concept, what does it mean from the hardware perspective? So, do we need any particular hardware accelerators to support HAI?
Yes, of course, we are going to need this special hardware because basically we are dealing with a kind of application that requires a high-performance system and circuit, and that's going to, with some constraints related to area, related to power consumption. And in that sense, you need to deal with that. So also, if you think about the design of this hardware to attain all this high demand in terms of computation power, you need to have to integrate several kind of circuits and several different kind of technologies. And this is also a big challenge in terms of hardware design. And the other aspect is related to the deployment of this hardware, because basically you have to consider aspects related to the environment where they are going to be deployed. You have to consider that these devices are going to degrade during lifetime. So, yes, to answer your questions, yes, we have several challenges, and we need to be able to design a new hardware for attending the demand of AI applications.
Mm-hmm.
Yes, I also concur because I think we are seeing the same needs that we saw in the past for other application contexts, where we started by optimizing general architectures that could be in the paradigm of one fits all. But here, the resources and the constraints are such that we can start taking all of them in account as soon as possible to try to optimize the overall solution, not just the software that has a lot of requirements in terms of being effective and high performance in terms of the accuracy and so on. So since you leverage on the available resources in terms of the quality of the computation, you have to deal with the requirements and the availability of the platforms you have. So indeed, in order to optimize the overall result, you have to tailor every single piece and working on the hardware, which is from a certain point of view, the enabling technology. It's just like we have been talking or hearing about AI since the previous century, but the key enabling technology was the computing power that the new and recent architectures put on the table so that the running AI is actually something we can afford. So in order to stretch and go towards the edge, I think that it is fundamental to be able to further tailor the hardware platform to be able to leverage the high amount of resources needed to perform well with the AI. Mm-hmm. There are several facets, but the platform is a key one.
But interestingly, a trustworthy AI system, among other aspects, also implies that it is reliable or resilient to hardware faults, right? And maybe could you outline which are the main threats which we need to take into account when it comes to the hardware faults?
Well, in this case, you have limited resources, and usually reliability requires overheads with respect to the nominal computation that poses certain, let's say, limitations in normal and not so critical environments. Here, we have the need for reliable and trustworthy computation on top of limited distributed resources, privacy-related or security-related assets, limited, let's say, impact from the environmental point of view. So even more, it will be quite a challenge to be able to put on top of the nominal computation a reliable one, so extra activity to make sure that no matter what the hardware is going to perform because of eventual failures, you still have a reliable computation output.
But what kind of faults should be afraid of? So what can cause this misbehavior of hardware?
Well, the single event upsets and radiations are going to be still even more impactful than in the past. I think that the smaller sizes is going to be something that actually also affects the overall computation. Not to say if you have limited power or resources, that's something you want to be able to deal with also, because we are thinking about portable devices with limited maybe energy budgets. So all the things that actually mine the normal behavior of computing systems are also increased and even more critical for edge AI, where the resources are limited. Maybe one potential benefit is to think that in this paradigm, you have many different resources contributing to the overall computation. So maybe you will benefit from redundant resources that were not meant for the specific tasks, but are there to contribute to the overall functionality and reliability of the overall system. So maybe you can benefit from that.
Mm-hmm.
Regarding this aspect, basically, if you think about some kind of resiliency or fault tolerance, you are talking about adding some kind of redundancy. You needed to have that. But the point is that if you think the applications that you are targeting with these new emerging devices, is that today we have this complexity of the AI hardware architectures. And I believe that we also needed to think about these aspects, quality, reliability, already during the design phase, which means that you needed to be able to, let's say, adopt a more holistic approach where you properly understand your hardware, the way that your hardware is going to behave in different kind of environments. And in that sense, at design phase, being able to already add some extra features to deal with that. So basically, it changes the perspective of how you are going to design this hardware. So I believe that we are going to have in the next year something much more is application-oriented design. Okay, so I don't see that you are going to have like a general design, and this hardware can be, let's say, the best solution for all applications. You need to think about the application. So in that sense, you can understand. And the other aspect that's really important is that due to the technology scaling, but also due to the fact that today we are putting together different kind of circuits with different technologies, you need to properly understand the source of these reliability issues. Exactly. Okay, so this is really important to deal with.
But to address reliability, which is related to hardware faults, to the sources, so can we also do something already at the model level? So even before we deploy it to hardware?
Yes, I think so. I think that know the technology is really important. Okay, so this knowledge related to what is the behavior of the technology in different kind of environments is really important. In that sense, of course, you can extrapolate this behavior in different abstraction levels, and you can deal with that. You can understand what is going to happen, and in field with this kind of device. When you put today some kind of emerging technology, it's like this gap, okay, or between what is happening at device level and what's observed at system level. We still needed to work to, let's say, to address this aspect, because we are not sure if something that's happened at device level, how it is going to be propagated at circuitry, at architecture level, and at system level. So it's the challenge is even bigger when you put it together, not only CMOS, but other emerging technologies. But I think that that's the only way. You needed to deal with that already during the design in different abstraction levels, to simplify also and to have a kind of early analysis so you can properly design.
Mm-hmm.
Yes, I concur, because I think it's necessary to fill the gap between the lower abstraction levels and the models you were mentioning. Also because the complexity when working at different abstraction level is completely different. So I think it is too complex to work all the way at the low level of the technology and of the hardware, thinking of dealing with applications that are as complex as the applications we are seeing today, and that they will get even more complex. So we need to fill the gap to be able to model the misbehaviors caused by the underlying hardware at the high abstraction level, to be able to explore in a realistic way what the system may suffer. Keeping in mind that we are also dealing with applications for which there is also an inherent degree of tolerance of the misbehaviors by computation. So maybe it's not so complex to say that we need to be perfectly catching and mitigating all problems. It will be even more complex to say what's going to be tolerated no matter what, because it has not let's say a critical impact on the final computation. At the same level, as the technology gets more complicated, it's necessary to fill the gap between what happens below and what we observe at the higher level.
Yeah, I agree with you. So one of the interesting topics that we face when we talk about HI is a relatively new trend towards neuromorphic computing. Last week I had an opportunity to visit a partner of the TAICHIP project, University of Manchester, and the team of Professor Davide Bertozzi, where they have a very interesting emulator for so-called spiking neural networks, right? It's a brain-inspired technology which is so exciting, and it has so many promising advantages when it's deployed for HI. And so I know, Leticia, that recently you joined IHP as a leader for neuromorphic computing team. So maybe you can explain us a little bit about neuromorphic computing and what are the key advantages.
Mm-hmm. So basically, the fact that you can have a kind of system with hardware, a specific hardware that can, in that sense, learn, adapt according to the environment, and in that sense, mimic our brain is really amazing. However, to have such a hardware, we needed to think that this is we have to develop your analog devices, okay? Which means that we are not going to compute the information in a digital way anymore, okay? So you have to deal with a kind of device that allow us to have several states, not just 0 and 1, okay?
Digital.
And this is really challenging. So if you think about how you can do that, Okay, so there are some platforms that were developing using the classic CMOS technology for doing that. This kind of to mimic this kind of behavior, but also if today we let's say see as really promising these emerging technologies such as resistive runs that you can implement this analog behavior. So, but the point is that to reach this, you needed to deal with several issues related to manufacturing variability, related to the reliability in field as well. Because if you are going to have more than one state, okay, you are dealing with multiple states, you needed to think that the stability and how to represent that it's a big challenge in terms of design. So neuromorphic hardware is not so simple. The idea is really promising and amazing, but we still have several steps to reach that point to have a hardware that can properly mimic the brain or something like that.
So what are the key challenges?
The key challenges is to find a proper technology. Okay, if you think about today, resistive runs is one really promising technology for implementing neuromorphic computing. So if you need to manufacture these novel devices to integrate them, the key challenge is manufacturing variability. The integration and the interface with the CMOS technology as well, because you needed to build all these modules, these ADCs, and that have to collect this information that's analog. And the other point is that if you are going to have devices that have a huge variability at time zero, and also if you put that device, if you deploy in different environments, they are going to degrade. They are going to be susceptible. And today we still do not understand what is exactly the susceptibility of these devices. We still are trying to understand what would be the tolerated variability at time zero for this kind of devices. So I think that we have huge challenges related to the immature manufacturing process. Even if you have today some high volume production of resistive runs, and also at the TAICHIP we are able to manufacture the device integrating with our technology, still we have a lot of challenges to guarantee that this device at time zero have a acceptable behavior, a tolerated variability, and then in field, when you consider all time dependent deviations, it's still a big challenge.
Okay, so that's why we still call them emerging technologies, right? So we need to give them a little bit of time, but still it's a very nice opportunity for researchers to contribute at this stage. Okay, so one of the other, I think, critical questions that our community and society and citizens are worried, maybe a little bit, and concerned is why in Europe we need to boost capacity for chip design ourselves, right? Generally for chip design, but also maybe specifically for efficient AI chip design. So what are the key reasons to do this?
Well, I think that gaining independence from outside of Europe production of chips is very important for everybody in Europe to be able, first of all, to have our own products and make sure that we actually exploit them as we deem best. I think we have a long-term competence in designing chips. Maybe in the past we somehow left the room to others and relied on the fact that others could provide the chips and so on. But given the instability, the general instability, and the fact that anyway we have that competence is indeed fundamental for Europe to regain a place in the production and the design and production of chips. So I think that this is a urgent matter for everybody. Also, if we are talking about chips that need to be tailored for the application environment and the application field we are thinking, with so much at stake for the applications we are mentioning, not only in terms of the, let's say, expected functionalities, but also the impacts and the side effects of the same technologies. I think it is really important for us to be able to drive the research and the development of this kind of area. So to be in control of what we are getting and what we are using. It's important to know how you design it, what you put in it, and how the technology can be used. Technology is never neutral, it's how you use it. So you have to be forward thinking about being in charge of what you get.
So, Cristiana and Leticia, from your experience in your countries, are there any particular practices that you believe that Estonia could benefit? So did you notice something interesting in the development of the chip design domain that we could learn from?
I don't see any, let's say, specific action that, but the point for me is that for reaching that point and to have this background for chip design, one key aspect, in my opinion, is collaboration. Okay. We are facing, we needed to be able to design very, very complex systems, circuits, okay, and systems. So, and for doing that, we are talking, we needed some expertise from the material, from the technology guys, from the design, from hardware, from software, from the application. So we needed to be able to build this kind of collaboration and to properly address all these issues. And I also believe that this kind of partnership is really useful, because in that sense you are putting together several expertise and different, let's say, perspectives of how to deal with the same problem. So I would say that from my perspective, the recipe is collaborate. Okay? We cannot develop these very complex hardware and systems if you don't collaborate. Okay, it's impossible, in my opinion.
Okay. So I think that the approach that we have these days with the TAICHIP project, where we collaborate not only with University of Manchester that I mentioned, with IHP Microelectronics in Germany, but also with other two strong universities, École Centrale Lyon in France and ETH Zurich in the Switzerland. It's in line with what you are suggesting, and it's really very beneficial and promising for our researchers. Okay, thank you so much. It was a pleasure to talk to you. Thank you for coming.
Thank you very much.